Welcome back to ROBT402 Robotic Mechatronic System Design course, Lecture 8, I/O Interface to PLC. Today's topics are as follow. List and describe the functions of the hardware components. Describe the basic circuitry and application for discrete and analog I/O modules. Describe specifications of I/O modules. Identify the functions of electromagnetic relays, contactors, and the motor starters. Identify commonly used switches in PLC installations, and explain the operation of sensors and output control devices. The I/O section. The input-output section of a PLC is the section to which all field devices are connected and provides the interface between them and the CPU. So here we have a CPU, inputs and outputs. Input-output arrangements are built into a fixed PLC. This is a fixed PLC, and this one is a modular PLC. Modular types use external I/O modules that plug into the PLC. Rack-based I/O section made up of individual I/O modules. So you see on the rack, we could have input-output modules installed separately. Input interface modules accept signals from the machine or process devices and convert them into signals that can be used by the controller. Output interface modules convert controller signals into external signals used to control the machine or process. The ability to locate the I/O modules near the field devices minimizes the amount of wiring required. The remote rack is linked to the local rack through a pair of communication modules. So here we have a local I/O, and here we have the remote I/O, and you could see the communication. Okay, so the remote I/O basically gathers all the inputs or distribute all the outputs to the local machine, and then communicate all the data once with the, let's say, one communication protocol like Ethernet to the local I/O or PLC. A rack is referred to as a remote rack when it's located away from the processor module. Okay, so this remote rack is away from the processor module. An I/O module is made of a printed circuit board and a terminal assembly. The printed circuit board contains electric circuitry. The terminal assembly is used for making field wiring connections. So we had this discussion, extended discussion before on the I/O racks, so that's why I'm basically passing these slides quite quick. Most PLC modules have plug-in wiring terminal strips that plug into the actual module. If there is a problem with the module, the entire strip is removed, a new module is inserted, and the terminal block is plugged into the new module. The I/O module can be 8, 16, 32, or 64-point cards. The points refers to the number of inputs and outputs available. A high-density 64-point card provides a greater space saving, but with less rated current output per outputs. Discrete I/O modules. So when we say discrete, we mean digital I/O. The discrete I/O interface module connects field input devices of the on-off nature, or 0 and 1. Okay, so 1 for on and 0 for off. The classification of discrete I/O covers bit-oriented inputs and outputs. Okay, so you see that we have this PLC and we have some discrete inputs and outputs. For example, inputs examples are push buttons, selector switch, limit switches, and proximity sensors. So by nature, they could either just send 0 or 1 to the PLC. And for the output, we have indicator light, signaling column, relays, and motor starters. Each discrete I/O module is powered by some field supplied voltage source. Since these voltages can be of different magnitude or type, I/O modules are available at various AC and DC voltage rating. So we could have AC or DC voltage, and you see that we could have a wide range of the voltages, let's say from 12 to 230 volt. AC and DC for the input and output interfaces. So we should be selective of our output card and see what voltage we need for that input or output device. The modules themselves receive their voltage and current for proper operation from the back plane of the rack enclosure into which they are inserted. So here is the back plane, and you could see that we have a power supply. So the card itself gets the power from the power supply in the back plane. The back plane power is provided by the PLC module power supply and is used to power the electronics that reside on the I/O module circuit board. Currents required by the loads are normally provided by user-supplied power. AC discrete input module block diagram. So you could see the block diagram for the discrete input module. The circuit is made up of a power section and the logic section. So here we have the power section and the logic section. An optical isolator is used to provide electrical isolation between the power and logical circuitry. So here we have the optical isolator here between the power and the logical. So you see the power, why do we call it power? Because the voltage could be high on the power side, and on the other side, on the logical part, usually we have the low voltage DC. However, on the power side, we could have a high voltage, even AC. The input LED turns on and off, indicating the status of the input device. Okay, so there is usually an LED on the module that shows if the module is on or off. AC discrete input module schematic diagram. So here we have the schematic diagram for the input module. You see the optical isolator here. You see the digital logic circuit and the power circuit. When the push button is closed, AC is applied to the bridge rectifier input. This is a bridge rectifier input. This results in a low-level DC output voltage that is applied across the LED of the optical isolator. So here is the LED inside the optical isolator, and here we have a receiver on the other side. When light from the LED strikes the photoresistor, it switches it into conduction. So when the LED is on, the sensor then receives the light, and then the photoresistor basically will be turned into conduction and will close the circuit. For the output module, we have almost the same diagram. We have the power side and we have the logic side and we have the optical isolator. The module is composed of the power section and the logic section, coupled by an isolation circuit. The power output interface can be thought of as an electric switch that turns the output load device on and off. So we could see this is kind of like a switch that turns on and off the power side. Okay, so when the processor calls for the output load to be energized, a voltage is applied across the LED of the opto isolator. And this in turn triggers the triac AC semiconductor switch into conduction, allowing current to flow to the output load. So very similar again to the input module. We have a LED, we have a receiver that acts like a switch, this transistor here, and basically closes the circuit on the power side. Discrete output modules are used to turn field output devices either on or off. Okay, so again, they act like a switches that closes the circuit. Output modules can be purchased with a transistor, triac, or relay output. So we have transistor, triac, and relay output. So any of these acts like a switch that closes the circuit. Certain DCIO modules specify whether the module is designed for interfacing with current source or current sink devices. So we need to basically have a compliant either input or output modules with OR devices. If OR devices are current source, then the module should be current sink. And if devices are current sink, then the module should be current source. If the module is current sourcing module, then the input or output devices must be current sinking devices. So they should be opposite and they should be complementary of each other. If the module is a current sinking module, then the input or output device must be current sourcing device. Okay, so we are done with the discrete section. Now analog input-output modules. Analog input-output devices have an infinite number of values. So when we say infinite, because we just want to basically have a comparison with the discrete. So say discrete is for digitals and infinite is for analogs. And if we need to basically discretize it, we need to digitalize or analog input in cases needed. Typical analog inputs and outputs vary from 0 to 20 milliamps, 4 to 40 milliamps, or 0 to 10 volts. Okay, so these are the ranges. The analog input interface module accepts an analog signal and converts it to a digital signal. Okay, so the module accepts or provides analog signal, depends if that the module is input module or output module, and converts it to the digital signal for the case of the input module and accepts basically digital signal from the PLC for the case of output module. The analog output module accepts a digital signal and converts it to an analog signal that operates the output. Electromagnetic control relays. A PLC was designed to replace control relays that made logic decisions. An electric relay is a magnetic switch which uses electromagnetism to switch contacts. So you see that we have a coil and contact here. This is a relay. Here we have an input circuit and we have an output circuit. When we close the input circuit with the basically electromagnetic field between them, the contact will be closed and the circuit on the output module will be closed. So why do we use this? We usually use these type of circuits to operate only with the low voltage DC to control or switch on and off a high voltage circuit. Okay, so here we have one type of relay. Okay, so you see that it's de-energized here and here is energized. De-energized means that the low voltage circuit is open. Okay, once it's de-energized, there is no any magnetic field between the armature and the coil. However, when the circuit is closed and is energized, we have a magnetic field, and the circuit will be closed by attracting the armature to the coil. So this is one type of relay. Of course, there are a variety of the relays on the market. This is one YouTube link that you could watch and enjoy learning about relay operations. Normally open and normally closed contacts. So here we have a coil and we have an armature, coil and armature here. And here is a movable contact. Okay, so it's just a matter of energizing the coil and attracting the armature, as you could see here. We could have two types of contacts. One is normally open. Okay, so normally open, it means that when the coil is de-energized, then the switch is open. So this is the normal condition of the switch. And the normally closed one is closed when the coil is basically de-energized. And when we energize, of course, the status of these switches will change. Okay, but again, the type of the switch will remain normally closed because in the normal condition, the coil is de-energized. So normally contacts are open when the coil is de-energized and closed when the coil is energized. And normally closed contacts are closed when the coil is de-energized and open when the coil is energized. Relay symbols. CR is used for control relays. Okay, so CR stands for control relays. Control relay used to control two pilot lights. So here on this circuit, you see that the switch open and the coil is de-energized. So here the switch is open and the control relay is de-energized. So once the control relay is de-energized, once it's, for example, is connected to a one red pilot light, of course the light will be off. And if we use the negated contact here, so here is what? It's normally open control relay. So let's assume that we have a normally closed control relay here, and once the switch is open, then the green pilot light will be on. Okay. On the other hand, we could have the coil energized. Okay, so here's coil energized for the normally open one. Now the red light is on. And for normally closed one, the the green light now is off. We call these normally closed one negated contact. So we could say this is a negated contact. Manually operated switches. Manually operated switches are controlled by hand. These are the different type of manually operated switches: normally open, normally close, and break make. Makes a circuit when it is pressed and returns to its open position when the bottom is released. So you see from the symbol, we have two type of standards, IEC and NEMA. And each of electrical devices have their own symbols. In Festoffloyd sim, you could see these symbols and identify your switches based on the symbol. For example, here IEC switch, it shows that the switch is normally open, yes, so because it's open, and the normally closed one, you see that the switch is closed. Normally closed opens the circuit when it's pressed and returns to the closed position when the bottom is released. And finally, we have the break make. So it could have either of these positions. So it depends on what normal or initial positions we wish to have. When the bottom is pressed, the top contacts open before the bottom contacts are closed, yes? So it really depends on our wiring and on our circuit, and it could act like a normally open or normally closed circuit. Or it could basically switches us between two possible positions. A selector switch operator is rotated instead of push to open and close contacts of the attached contact block. So you see that we have for example, three positions here, three possible positions. Okay, so we have two contacts A and B on position 1. The contact A is closed. On the position 3, contact B is closed, and on position 2, for example, none of them on this specific case are closed. So they are used mostly for on-off auto or hand-off auto. These three basically positions on machines. Mechanically operated switches. A mechanically operated switch is controlled automatically by factors such as pressure, position, or temperature. So what is the differences? The trigger here is mechanic but not manual, okay, so don't get confused between these two. Mechanic means that, for example, a moving object or a temperature or a pressure. But when we say manual, it means that the operator himself or herself closes or opens that switch. Okay, so one example of mechanically operated switches are limit switches, are designed to operate only when a predetermined limit is reached. And they are usually actuated by contact with an object such as cam. So we have a cam and follower. For example, here this is a cam, this is a follower, and the cam and follower is a perfect example of a limit switch. So we have a moving object, and that moving object in this case is cam. That could be, for example, a rod or a piston. Okay, so that's a moving object which basically switches or pushes or triggers or switch. Okay, so the NEMA symbols we have for the normally open limit switch and the normally closed limit switches. Okay, so these are two type of the switches we have, and IEC symbols. So you see that they are slightly different from those manual symbols. Pressure switches are used to control the pressure of liquid or gases. They are designed to open or close their contacts when a specified pressure is reached and can be pneumatically or hydraulically actuated. So here we have a normally open contact, normally closed contact. These are all pressure switches. This is an NEMA switch. This is IEC switches. Okay, so you see that how they represent the pressure switch. Sensors. The method of connecting a proximity sensors varied with the type of sensor and its application. So here, for example, we have 3-wire sensor or 2-wire sensor. It's beyond the topic of our lecture to go to the detail of wiring and the different type of wiring here, but just basically this slide shows us a variety of for example, proximity sensors and how they could be connected in case of the 3-wire or 2-wire systems. Output control devices. Symbols for output control devices. All the devices here on this slide are output devices. Pilot light, control relay, which could be normally open or normally closed, and the motor starter coil, and motor overload relay contact or OL, and is usually negated contact. What it does basically, when the motor is overloaded, then it will shut the motor off. Symbols for output control devices continues here on this slide. We have an alarm, we have a heater, we have a solenoid valve, motor, and horn. So just look at the symbols, solenoid and the valve and the motor and the horn, and remember what they represent. An actuator is a device that converts an electrical signal into mechanical movement. An electromechanical solenoid is an actuator that uses electrical energy to magnetically cause mechanical control action. Okay, so quite simple. We have a coil, we have a plunger, and we are using electrical energy to move a plunger or convert it to a mechanical energy. And this is what we call solenoid. Solenoid valves are electromechanical devices that work by passing an electrical current through a coil, thereby changing the state of the valve. Okay, so here we have a coil, for example, here is de-energized, and we have a plunger that opens and closes the opening of the valve. And you see the symbol here, okay, for the solenoid coil and for the limit switch. Okay, so this is a limit switch and this is a solenoid coil. And here now we have a coil energized, and for these cases closed. The valve is closed by the plunger. Process used to control the level of water in a storage tank. We have a manual mode in this case and the automatic mode. Okay, so this is one example, okay, that we want to go through and see what input and output devices could be used. What are the input devices? On and off switch, the auto manual switch. These are the input to the system, plus we have a high sensor switch and the low sensor switch. These are also input to the PLC. What are the output devices? The pilot lights here, green, red, and yellow, and the pump. The manual mode, the pump will start if the water in the tank is at any level except low. Okay. So we could basically manually turn on the pump if the level of water is above low sensor. This is the manual mode, okay? Just turning on and off the pump on the manual mode, so this switch should be on the manual. But what if you put it on the auto? Then when the level of water reaches the high point, the pump will start, okay, to pump the water out the tank, okay? And when the water level reaches the low point, the pump will stop, okay? So this is the auto mode, okay? So we want to see how we could program or PLC or design or relay circuit. Okay, so here we have basically ladder logic programming. We have input devices, the on and off, the auto manual, the low sensor switch, and the high sensor switch. And the output devices, we have a motor and pump running, for example, for 3 pilot lights, and the green indicates the pump is running, the red indicates the low level of water, and the yellow indicates high level of water in the tank. Okay, so let's go through the program. Okay, so this is for the manual auto. Okay, so yeah. Okay, so for the manual mode, you see when the low sensor switch is on, so the level of water is above the low, then we have this capability of turning on and off the motor by the on-off switch. But if the manual auto is on the auto, then basically all these wrong here will be basically false, and the motor cannot be turned to the on and off. Okay, once we switch to the auto, it will basically latch the motor, so it will override the manual command. Okay, so now let's say we are on the auto and the sensor is reached to the high, so it will latch the coil. It means that it will keep the coil on, it will keep the pump on, and the motor will basically continue running because you see the latch here is on. And once basically the level of water reaches to the low, it will unlatch the coil, and the motor will be off. Once the motor is running, then the green pilot light is on. Once we have reached to the low sensor, then the red is on, and once we have reached to the high sensor, then the yellow is on. I/O connections for program. So for the previous basically example, we have the I/O connection, we have the input devices and output devices, and see how we have connected them to the input and output module of the PLC. For example, the on-off switch is connected to the input 0. Okay. The manual auto is connected to the input 4. Okay. So once we know our connection, we know the address of our input or output devices, in the memory of PLC, and we could use that address in our programming, okay, any type of PLC programmings. Okay, so here, for example, the low level is on and is connected to the output 9. You see the indicator light on the module is on. And so we have LED indicators on the front panel of the input and output devices. So it helps the operator or the programmer to diagnose and understand which input and output devices are on and off, and could either diagnose or basically improve the program and so on and so forth. Okay, so sensors could be either PNP or MPN configuration, could be current sourcing or current sinking sensors. So when we have a PNP sensor, the input module of the PLC also should match the type of the sensor. Okay, so for just an example here, we go through the digital input module of the PLC we have in the lab. I know you don't have access to the lab on the MPS 500 system, but however, I think it's a very good example to show what you should basically expect of an input or output module. So first, this is digital input or the discrete input, so it means that it only accepts the digital inputs, or could be connected only to the digital switches and sensors. We have basically, so we could basically just insert it on the rack, okay, and we could add as many as these inputs to our PLC if the rack has enough space and room. So you see that we have those LED for diagnostics, okay, that shows if the device is working and is connecting to the rack. We have basically LED for channel status. It means that, for example, here we have only 8 channels, if I don't mistake. Yeah, we have only 8 channels, and shows what are the status of those channels. If, for example, one switch is on, then the LED of that channel will be on. What else? For example, here we have a wiring diagram that shows what is the matrix exactly of the inputs, a label, and basically we have some other symbols which is not that important for us. Okay, so here again we have a status and the error displays. It shows, for example, for the diagnostic green and red, and the channel status green and channel error red, and the power green. Combination of basically these LEDs represent some type of error or warning, and we should refer to the manual. So here we have those LEDs. Meaning of those LEDs: for the diagnostic LED, one is off, flashing on, and the flash is red. So flash is green or flash is red. Okay, I'm not going to go through the whole detail of the table, because again, I'm just showing you this input module as an example. What should we expect from an input module? Other LEDs for LED channel status: hollow green or hollow red or solid green and basically solid red, and combination of them on and off shows something, so they have a meaning. And in case we encounter some issues, we should refer to the manual of these modules. For the power LED, again, when is on, simply the supply voltage is on, and when is off, the supply voltage is off. Okay, we are almost done with the digital input output and the analog input output modules. At the end of this video, I want to represent simulation of handling station in Fluid Sim, and I also expect you to do the simulation and submit it on Moodle. Okay, so what do we have on the handling station? I strongly recommend you to go and watch the videos on YouTube for the handling station. You see that we have a top crane, and there is one pneumatic cylinder for that. Okay. We have the vertical cylinder to reach the part, and we have a gripper. So we have three pneumatic actuators. We have check valves to control the speed on these two, plus we have these pilot non-return valves, and we have bunch of 3x2 or 5x2 directional valves, and we have solenoids 1M1, 1M2, 2M1, and 3M1. This one, you see that we have a group valve. These are the internal components and valves of that group valve. But if you want to simulate it in Fluid Sim, you don't need to basically have these complicated group valve. You could simply use these individual valves separately to simulate behavior of the handling station. For the electrical circuit, okay, we have sensors 1B1, 1B2, 1B3, 2B1, 2B2, 3B1, and we have a part available sensor for the gripper, and we have basically transmitter and receiver. Okay, so this is the receiver for basically on the station. This is on the station. You don't need to include this one, and this one is used to confirm connection of the handling station, for example, to the distribution station. Okay, so you don't need to include this one in your simulation. Look at the symbol of them, okay, and remember from the sensor session, what do they exactly represent? Okay, so we have here solenoids 1M1, 1M2, 2M1, 3M1. Okay, and okay, so this is the electrical circuit for that part. Okay, here is our Fluid Sim simulation. Okay, this is for the pneumatics section. Here is for the sensor section. Here is for the solenoid section, and here we have our PLC. Simply here, we are not using a complicated circuit, although you could, or you could program with codices, or here you could have a graph programming here inside a Fluid Sim. but instead I'm using a very simple logic inside the PLC, and I will show you. So I expect you basically to build this circuit as well and submit it on Moodle. Here, if you double click on the PLC, and this is the circuit, the logical circuit I design, you could basically come up with a different circuit, set reset and reset set. Basically, blocks are used between the input and output to have a proper sequence and logic. Okay, so far we presented a simulation of handling station. Was a perfect example of how we could simulate the pneumatic, the sensors, and the electrical circuit all together, and how we could implement the simple logic. Now I expect you to simulate the testing stations and other stations. Of the MPS 500. So again, I recommend you to watch the videos and see what we have. For example, on the testing station, we have this elevator, we have that pneumatic cylinder that kicks the part out to the slide, and then we have the pneumatic slide that we blow the air underneath of the part, and the slide will the parts will slide down to the pallet. For the testing station, here you see the sensor connections and the circuit, and you could also see the solenoid connections. For the testing station, if you want to make it more complicated, then we could have also the comparator. So you could also include the comparator if you could in your simulation. Otherwise, you could just simply exclude it for sake of the simulation at this stage. And the sorting station, again, we have the pneumatic circuit brought to us by Festo. Here is basically the first guide, the second guide, and here we have our single acting actuator that keeps the part at the beginning of the conveyor for checking the color and availability and the material. Okay, so watch the videos again for the sensor and here for the solenoids. So I expect you to submit the handling station that I already basically show you how to model it. Okay, so that could be quite easy. That is an example. Then I expect you to submit testing and sorting station as an exercise.